We tend to perceive only what's familiar, so when new discoveries open up unfamiliar worlds, they present us with a dilemma. To see new worlds accurately may require a radical step: the suspension of prior beliefs. Now let's start with what's familiar. Prior ideas, experiences, and memories form the foundation of our thinking. They make up what's familiar. What's familiar is things we bump into and think of as solid. Other things we splash in and think of as a liquid. And a few things we feel blowing past us and think of as gas. What's familiar is thinking of these things as made up of atoms. Atoms that have mass. Atoms that have positively charged particles on the inside and negatively charged particles on the outside. Atoms that can gain and lose these particles, but that have few electrical effects. What's familiar is the accumulation of our thinking and acting and remembering as creatures who live on the surface of a wet, rocky body called Earth. But there are things and events above the surface and below the surface, and even on the surface, that we have not thought about or remembered. Not long ago, our ancestors thought differently about things and remembered events differently. What was familiar for them was not thinking in terms of solids, liquids, and gases, but thinking in terms of earth, water, air, and fire. And if what's familiar has changed before, it can change again. For some time now, we've been accumulating unfamiliar experiences above the surface. Early in the 20th century, we began to discover atoms that were unfamiliar because they are missing one or more negatively charged particles. The remaining portions of these atoms are positively charged. The presence of these negatively and positively charged particles is the distinguishing characteristic of what we now call plasma. In the second half of the 20th century, we discovered that plasma fills the space between planets and stars. Plasma behaves in unfamiliar ways, but our habits of perception can make it difficult to see plasma as something completely different from a gas. Its similarities to gas are overshadowed by its dissimilarities, and if we can break free from prior ideas about gases, we can make the unfamiliar ways of plasma familiar, and we can see a new universe. A charged particle that moves is an electric current. This is a familiar thought when we're doing electrical things, but we've not thought about it when we're doing things in space. An electric current is accompanied by a magnetic field that wraps around the current and gets weaker with the distance from the current. With more charged particles moving in the same direction and moving faster, the magnetic field gets stronger. Again, this is a familiar thought when we're doing electrical things. But when astronomers discovered magnetic fields in space, they were surprised and mystified about how to explain them. They tried to conjure magnetism out of gravity and mass. Because the charged particles are moving through this magnetic field that gets stronger toward the axis of movement, particles that are not moving exactly along the axis are squeezed toward the axis. Plasma scientists call this the pinch effect. Outlying charged particles, together with the neutral atoms they bump into, are pulled into the current channel. Outlying areas are depleted and the channel gets denser. It self-constricts until the gas pressure on the inside balances the magnetic pressure on the outside. This balance of pressure along the axis produces long, thin filaments of matter that are sharply separated from their rarefied environments. We remember that this is what happens in a lightning stroke, or at least this is how we think about what happens in a lightning stroke, and it seems familiar. We understand. But we had not thought about this happening in space. Christian Birkeland thought this might be what happens in the aurora. He trekked to the Arctic Circle to measure the magnetic fields from the constricted channels that made up the auroral currents. These Birkeland currents were later named after him. He speculated that this might be what happens in the filaments that make up the solar prominences and the solar corona. He thought the filaments might carry electric currents from the sun to the earth. Such ideas were too unfamiliar for astronomers conditioned to think in terms of gravity and mass. They clung to their familiar ideas of mass particles until artificial satellites orbited through and measured the electrical filaments that were the auroral currents. Even then, the idea was too unfamiliar for them to recognize that the moving charged particles from the sun were also currents. And because gravity-oriented astronomers are familiar with moving masses, they seldom think about charges. What's not familiar, what has no conceptual framework for understanding, is often not even perceived. So they think of moving charged particles from the sun as a wind instead of an electric current. They think of charged particles falling on a planet or on a moon as a rain instead of an electric discharge. They think of charged particles moving along a magnetic field as a jet instead of a field-aligned power cable. And they think of abrupt changes in the density and speed of charged particles as a shock front instead of a double layer that can dissipate electrical energy and even explode. They can't see the electrical particle forest for the mass particle trees. They're lost in a plasma universe, seeing charged particles in motion, but thinking in terms of gas, kinetics, and gravity. Plasma cosmologists think differently. They remember their experience with currents in a laboratory. They are familiar with the right-hand rule. When they point the thumb of their right hand in the direction of the current, their fingers will curl in the direction of the magnetic field. In the space between the two parallel currents, the two magnetic fields will have opposite directions. Because north and south poles attract each other, the two currents will move toward each other. But as they get closer, the electric repulsion between them will become stronger than the magnetic attraction. The two currents will begin to twist around each other. Plasma cosmologists recognize these twisting filaments in the penumbra of sunspots and in coronal streamers. Space probes have detected them in a plasma tail from Venus that is identical to the ion tails of comets. The glowing filaments in so-called planetary nebulas and in misnamed supernova remnants are familiar. The jets from Herbig Haro stars and from active galaxies are familiar. Once electrical currents in space have become familiar, once they're understood, they can be perceived almost everywhere. The only place they're missing is from modern astronomical theories. But the experts posed a question once upon a time, and that question was, what will we see as telescope technology improves? Wal Thornhill's answer was, filaments. Filaments everywhere.